Alrighty, so in the last video, we talked about trying to approximate the total area underneath some function, underneath some curve, between 2 points, right, in kind of like this interval here from A to B. And we talked about doing that using what we called Riemann sums. And Riemann sums is a fancy way of saying we're adding up these rectangles. The number of rectangles that we use is at our own discretion. We get to pick. So in this example that I have here, I have cut up my interval into 4 pieces with the intention of using 4 rectangles to approximate the area under the curve. And that approximation manifests itself with this kind of little expression that we have on the right side. So remember that the sigma symbol right here means that we're going to add up some stuff. We're going to start counting from 1, and we're going to keep going 1, 2, 3, 4, 5, 6, 7, etc. until we hit whatever number n is. And the important thing is that this formula, as scary as it may have looked in the past, remember that this right here is just the height of some particular rectangle, and this bit right here was the width of one of our rectangles. And so just, again, to just remind us of where we just came from, the reason why there happens to be this x sub I star here is it's just to remind you that the x value that you pick really depends on if you're using a left Riemann sum, a right Riemann sum, or a midpoint Riemann sum. So for instance, in the example I have here, if I were to pick a rectangle, and let's just pick this second rectangle right here. So if I were to pick the rectangle that I could draw from here, I'm going to draw it either using the left endpoint, which would mean I would draw it using this, and I would create my rectangle like so. If I was using the right endpoint, then I would go up here, and I would draw it based on the right endpoint, like so. And if I was using the midpoint method, I would use the one right in the middle and create the rectangle just like so, okay? And so that's not too bad. That's, that this is where we're getting. So maybe I'll use the left endpoint just for the sake of illustration. So we get this rectangle right here, and we ask ourselves, what is the height? Well, we have to look and say maybe if we're using the left endpoint method, then this would be our first x value, and this would be our second x value, and then the next one over would be our third x value, right, dot, dot, dot. And so this particular point that I've selected here, this guy right here, would, have a point of whatever that x value is, and then whatever f of x2 happens to be, right? That would be the y value. And so that would give me that the height of this rectangle would just end up being whatever that y value is, f of x sub 2, for instance. And that's basically what this bit here says. The nice thing about calculating the delta, right, the delta x, is that the delta x is always the same for all the rectangles. That all we have to do to calculate this little delta x right here, our width, is we just take the total interval length, right? Remember, delta x is basically equal to the total length, and then we chop it up based on how many rectangles we have, and voila, we're going to get our width. So this is just a recap of what we did in the last video. And kind of where we left off was, how could we make this approximation better? What could we continue to do? And the result that we came up with was, or that maybe I alluded to, was that we could increase the number of rectangles, right? If I take this drawing and I take the number of interval, or the number of little maybe subintervals we have, and I cut them up into even more. So there's 4, but now I'm gonna, maybe now I got 8, and maybe I cut them up again, right? All again. Now I have 16, right? This looks even better because each individual rectangle, depending on what method I use, right? If I start adding more and more rectangles, you can kind of see that our guess that we're going to get, if I were to add up 16 individual, little tiny rectangular areas, our guess is going to be much better. And so we're going to say our guess improves. Our guess improves as n gets bigger, right? N gets bigger. Where n, remember that this n right here is the number of rectangles that we are choosing to use. Okay. And so, since we've taken calculus, we know that, this doesn't mean n is 100 or n is 1,000 or n is 1,000,000, right? The idea is that in theory, what this means is what we're really talking about here is we're talking about n approaching infinity. We're talking about examining what happens to this, right, as n approaches infinity, as we, in theory, start to take more and more rectangles. So let's kind of I'm going to rewrite this down here. So this means that our total area, in theory, will become a perfect guess if we're adding up all of these little heights, right? X sub i's. We have these little delta x's, these widths. But instead of going from 1 to n, we're going to use our calculus tool. And what tool am I alluding to? We're going to introduce the limit, right? The limit is a tool that we have that basically says, what do we expect this thing inside the parentheses to equal as n approaches infinity, right? And this, right, if you're just thinking about it purely in theory, if you're just thinking about it from the idea of drawing pictures of what's going on, this should be the exact area under the curve, right? This should do it for us. Okay? And so now the more interesting question is, well, what happens to this stuff? Like what does this even mean? How do I even evaluate something like this? And so now I get to drop a couple hammers on our heads, and they're going to be really, really useful notes for us. So the first thing that we're going to notice is, okay, well, if I have, right, infinitely many rectangles, okay, well, how many different x values do I need to basically calculate the heights for? Do I still have an x sub 1, an x sub 2? Do I have 20 of them, 100? How many? Excuse me. And so, well, the answer is I technically have infinitely many x values. I need to do this calculation. I need to do this height and width calculation for every single x value, which means that this is no longer counting 1, 2, 3, 4, 5 because I have infinitely many x's. So what's going to happen in this formula when I take a limit is this is just going to say, look, you give me an x value. I need to know what the height of my rectangle is at any x value, right, for any general x. So this, instead of being f of x sub I, where I'm picking just a couple of them, I need to do it for every single x value that is in this interval. For any particular random x, I need to be able to calculate the height. Now, the next thing that we need to look at is, okay, well, just logically speaking, what happens to this delta x, right? What's happening to the width of these rectangles? Well, we have, remember that the width is the total interval divided by the number of rectangles. What's going to happen to the size of this, right? Just think about it logically. What's happening to the width of each of these individual rectangles over here as I increase the number of them? And the answer is that width is going to get really, 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 really small. And it's going to approach 0. Right? It's going to approach 0. It's going to get really, really, really small. But obviously, if it equals 0, then, well, that doesn't really make much sense because, then you say, oh, these have width of 0 and the total area is 0 and blah. So instead of it being a delta x, right, what did we learn about in Calculus 1 that represents an infinitely small change in x? We learned that was dx. That dx, remember, means an infinitely, right, this is an infinitely small change in x, okay? And so that's going to be our new width. And so now the last bit that we have, like if we're trying to make sense of this equation, which again should make perfect intuitive sense, right? We're basically adding up all these rectangles, but now I don't want to add up a finite amount of them. I want to add up infinitely many rectangles. And so the question is, what the heck do I do with this? It turns out that this represents itself in mathematics with this symbol right here, and we call this the integral symbol. So this is what we call the integral symbol. Okay, and so that's what this means. This little expression right here, that little expression right there, literally says add up infinitely many tiny rectangles. So the integral itself literally means add up infinitely many tiny blanks, and those blanks, right, what are we adding up? It's just the height and width of a bunch of infinitely skinny rectangles. Okay, so what does this kind of look like? So let's give like a drawing here. So let's go back to our famous example of, here's the function f of x is equal to x squared. And so, if we were to like kind of try and conceptualize this, and if I want to say, find the total area from 1 to 5, so I want, what is this, the area of this region right here? How do I write this as an integral? Well, we say, okay, well, I need to do this for any x. There's going to be infinitely many tiny rectangles in here, and we have to add them all up for every single value of x in this interval. And so the way we do that is say, okay, well, what is the height of one of these arbitrary rectangles, right? What is the height of this guy right here? And well, at any given x, the height is going to be just the y value. It's going to be f of x. So we'd say, okay, well, the height, that's just going to be f of x. The width is going to be dx, right? The width, this tiny, small, infinitely small change in x here is dx. And what does it mean to add up infinitely many pieces of something? It's going to be this integral symbol here. And so we could write this out more succinctly as the integral of x squared dx. Okay, and so this is kind of how we would write this. The only thing that we haven't taken into account yet is what? Well, it's going to be these bounds, right? It's going to be the bounds 1 and 5. And so we would express this, we would identify that those are the bounds by writing a 1 here at the bottom and a 5 here up at the top. And this is kind of how we would interpret this little thing right here, right? This thing says the integral of x squared dx evaluated from x is 1 to x is equal to 5. Okay, but before we talk about how to evaluate those numbers, we'll do that in the next video. Let's kind of backtrack a second and let's try and make sense of this right here. The integral of x squared dx. Now, you may remember in the review video when I introduced the antiderivatives, I very briefly wrote this symbol down and then I erased it because I said I don't want you to get super confused. But it turns out that, yes, the other big reveal that I have is, how do you go about evaluating this, right? What does this even mean, right? What does this mean? How do I solve it, etc.? It turns out that this is synonymous with finding the antiderivative. Find the antiderivative of x squared. That's what it means. This integral symbol for us literally means add up infinitely many tiny things. But how do we do this? It turns out via some mathematics that you're welcome to look up on your own. It means take the antiderivative, find the antiderivative. And so if I were to try and evaluate this thing, this is going to equal x cubed over 3 plus c, right? This one, that's what we would get. And at this point, people tend to ask, well, what do we do about this dx? What does it mean? Do we have to have it there? For now, you can kind of think of the dx as basically telling us, it tells us what variable we are integrating with respect to. And what I mean by that is, do you remember in Calculus 1 when we had like y is equal to x squared? Every single time that we took a derivative, we had to specify we're taking the derivative with respect to x, because that lets me know that if I do that to the left side, I can only write it as dy dx. But if I do it to the right side, I get to write it as 2x, right? That I treat this one a little different because I'm taking the derivative with respect to x versus this one on the left. I'm just taking the derivative of y, and I can't really do that. So for now, you can just kind of think that even though it makes sense from the picture that we drew over here, that we need both of these things, right? This is still the height of an arbitrary rectangle. This is still the width of an arbitrary rectangle. If you're trying to think about it in terms of, why does it have to exist in order to do this calculation, if I do integral of x squared and I don't write anything here, we say this is like ill-defined, that I don't know what variable I'm trying to integrate with respect to, so it needs to have this dx here. So like, for instance, if I were to ask you to do the integral of, say, cosine of t dt, this lets me know, okay, I'm going to integrate this with respect to t. I want the antiderivative of this particular function, and you say, well, what function has a derivative of cosine? And we would quickly say that the answer is sine of t plus c, just like so. Okay, so now it's going to make a little bit more sense when you see this in the book, and you see this integral of some function with respect, dt, right? It could be anything. This variable could be anything, t, z, whatever it is. But this is kind of the math part of it. So there's two things that you need to walk away from this video with. One of which is you need to be able to understand where this integral is coming from. You need to be able to understand that it's coming from the idea of adding up a bunch of little teeny tiny rectangles on a particular given interval. And this particular integral that we've written here is what we call an indefinite integral. You may see that. I'll still just kind of refer to it as the integral, but it's indefinite because in the way I've written it, there are no bounds in it. And you can imagine, right? What do you think I call this integral over here? We call that a definite integral. And the way you can kind of differentiate the two is that an indefinite integral, you're going to get just like a function out for the answer. But a definite integral, again, in the context of the fact that we're trying to solve for total area here, in this particular example, then the definite integral, we're actually going to get some number out, or hopefully we get some number out in this particular context that we're dealing with right here. So that's going to do it for this video. Short and sweet, just an introduction to what the integral is, where it came from, what it really means. Really try and hone in on this bit right here, understanding that when we take the limit, basically we're just saying have an infinite number of rectangles now, that it magically turns into this integral symbol, and that there's a difference between doing the integral versus just doing the Riemann sums by themselves, right? Just doing those guys up there. Yeah, so that's going to do it, and I'll catch you all in the next video where we talk about how to work with the definite integral.